I'm excited to now kick off the final session of this conference, and we'll be talking about advances in generative AI and large language models. And I'm joined with Siddhartha, who is one of the co-founders of Abacus.AI and also the VP of Machine Learning and Research. So good morning.
Good morning. Yeah, hey, nice to see everyone, or see everyone. The last discussion, I got to catch a couple of the discussions before this. They're really interesting and really thought-provoking.
Mm-hmm. All right, great. So I'm excited to discuss generative AI and large language models. So there's been quite a lot of activity in this area, and quite a lot of really fascinating progress. So maybe we can start out so everyone's on the same page, explaining a little bit at a high level what large language models are, and a little bit of the history in the last few years. So would you like to take that question?
Yeah, sure. Right. So language models have been around in various forms in various applications. From translation, of course, was one of the big early applications around language, through things like entity recognition and so on. For a long time, LSTMs were the de facto standard for doing language models. There was this famous seminal paper that went with an alternate architecture from LSTMs to an architecture called transformers that allowed different parts of the input to mix much more freely than LSTM's sort of linear style mixing. I think that there was one very important side effect of this. The transformer architecture was very well suited to GPU compute, was very modular, very easy to stack, very easy to grow, and in different dimensions and sizes and so on. And so it became it became a really natural building block for a number of applications. And I think where it's of course shown the most is in language modeling. Large language, the language modeling, has gone with various objectives in trying to build the models. BERT, which is probably the first very well-known transformer-based architecture, used two different styles of training. Basically, one was to make the model guess the mask token in the middle of the text. The other one was to tell whether two sentences were from the same piece of text or not, roughly two sentences. All of that has kind of now in 2022 was definitely the year where large language models came out. I think everybody standardized on this one very simple, straightforward idea of predicting the next token in a piece of text and just throwing gobs and gobs of text at it. The web has made essentially the data available for this problem unlimited, and people started experimenting with how big a model they needed to train what percentage of the web, right? So people were talking meaningful percentages of the entire web corpus. And we ended up, we have some very well-known language models, and they're doing amazing things. I think if I 5-10 years ago, I think you asked someone that a model trained on predicting the next word would pass the Turing test, I think people would have said that seems very, very unlikely, but here we are. I think ChatGPT has passed the Turing test in a couple of different examples. I don't think it's artificial general, AGI is still the next goalpost, but it's surprising that such a simple idea, but backed by a lot of compute and a lot of data, can do so much.
Yeah, quite interesting how the field of large language models has progressed. I think to summarize a bit of what you said, the first really breakthrough paper in this area was Attention is All You Need, I think around 2017. And then shortly after that was the BERT architecture. And this was, masking out different words in a sentence and trying to predict the word that is hidden. But then more recently, and also all of this progress has really been driven by the rise of big data and GPUs and deep learning. So as we have more GPUs and more compute available, these models just get better and better. And then yeah, as you mentioned, the models have gotten actually, or at least the training process, you could say, has gotten even simpler recently, with only predicting the next word in the sequence. So not even masking out a random word, but just predicting the next word. And I think it's pretty interesting, where in a lot of other areas of machine learning, we see the architectures getting more and more complex. But in natural language, we see almost the opposite. There's still we're still seeing the benefit of just adding more data and compute, and that's not really slowing down. So we're just continuing with unsupervised learning and having a very simple training procedure, but the models are still improving. Do you think that'll start to slow down a little bit and we'll need to have more complex architectures, or do you think there's still a long way to go with just adding more and more data and compute?
Okay, so starting with one thing. So one important point we didn't cover in 2022 that I think went beyond the next word prediction. So the initial training of GPT and those flavors of models showed that they could really capture the structure of language on the web, but the output they produced was often not very readable. You could tell it's coming out of a computer. So I think the big innovation that people have discussed a lot now is this instruct training, or some kind of reinforcement training, where you have a model that basically understands language on the web, but then you want it to produce outputs in a way that is pleasant, or there's some kind of value function. And so then the second piece of this puzzle is learning the value function from some sample text, saying this is how humans talk, this is how a conversation goes. Then you fine tune this model, or you further optimize this model to produce text that is valuable. So that's one big addition that I think really has made these models, when you read it, really stand out and say, oh, this is really cool. This looks like it's written by a human. But in terms of the architecture complexity, I don't think so. I mean, I don't see architectures necessarily getting more complicated in this space. At the end of the day, I mean, very early on, people showed that in neural networks, wide or deep networks are effectively equivalent. I mean, there's a question of how convenient they're to train, whether they'll actually work, or whether you can get convergence. But mathematically, both of them will represent, can represent our universal function approximator. So what are we doing by building these increasingly complex architectures, or increasingly baroque architectures? I don't think that was not where value was being added. So now I think people have found an architecture that works well on our current silicon, on our current chip designs, is easy to stitch together, is easy to stack, and is frankly even easy to share. I think one of the nice things about the transformer architecture is each block is a very well-defined module, so you can pull it apart or train it in pieces, various things like that. So I don't see that going away. I do think that if our compute infrastructure changes, if there's some fundamental innovation coming out of our GPUs, or Intel's next neural architecture thing, that might motivate a reason to come up with a different block, different model. We're seeing some of those things at the level of floating point number representations, right? So as you got these really big architectures, we're running into memory limits of a GPU. So people are talking about different float encodings that are better at high dynamic range. So I think those kind of changes will come, but fundamentally, I think we want an architecture that the piece basically all of the input can see each other, and things will work. One last thing there is maybe context length. So the amount of data you can feed the model is a constraint. So you want to be able to let it see as much of the data. So people are innovating in sparse attention, or those kind of things, which are still the same building blocks, but being clever about how you organize the flow of information through those building blocks. Almost like chip design, frankly, actually. It's beginning to look more and more like chip design, some of these LLM architectures.
Got it. Okay, so you're saying, so yeah, there is a bit more complexity to the training with instruct training. And then also the second part of your answer was really, it almost reminded me of this concept of the hardware lottery, where the architectures that we've converged on currently for language models are really because they're convenient for a variety of side reasons, like how they work so well with GPUs, and also other reasons, like the transformer is easily modular and we can fine tune it easily and things like that. So yeah, that makes sense. So then would you say that so what do you think is the biggest bottleneck now then? Is it really engineering effort and yeah, scaling up some of the compute and engineering, or do you think there's another bottleneck for really progressing language models even further?
I think there is there are a couple of different bottlenecks. I think one of them is this value function. So right now, the way that value function is produced is you take a couple of so I think these companies that have built really good models have actually paid and not well have put in the money to build the initial training data sets to train these value functions, right? Like collecting chats or getting human labelers to generate ideal responses. All of those things which are quite expensive, right? To actually get a person to write like what is the right answer to this question. So innovation in like how to like efficiently build these value functions so you can tune the model is, I think, one side. I think one area that's very interesting that is probably close to your heart is like how to do the compute trade-off, right? So training each of these is an expensive affair. You have to make decisions upfront about where you're going to spend your money. There's these various scaling laws, like, do you spend time processing more data, or do you spend time on larger models that take more compute to run each example? I think that I think that there's more interesting things on sort of the data side and like collecting more interesting data. I think you're going to come to, we will talk about it later, but like, in the context of like generating code and so on, like there's really interesting questions like, does the model actually learn that variables have to exist in the context that you can, what does it mean to understand that like a variable has to be used only after it's defined? It's there in all the code that you read, and like that's kind of like reflected in the property, but how much data do you need to train the model to do that? Do you really need like website corpus? It seems like a simple enough concept to learn, but yeah, there's a question of data efficiency. Like I feel like right now there is, where it's working, but in a fairly data inefficient way. It shouldn't take so many examples to train the model about the grammar of a language.
Absolutely. Yeah, it seems like being able to process data effectively would be important to moving language models to the next level. It also reminds me of some thought that I've had. I think you have much more experience with language models than I do, but one of the things I wonder is, so for example, GPT-3 showed that just by predicting the next token, they're already able to add 3-digit numbers and do some basic logic reasoning. But what do you think about some language model with some sort of logic architecture built in, so that it actually could much more easily do things like add 3-digit numbers, and maybe that would even help with code generation, where it's able to really understand the concept of having a variable, and this variable will be the same later on in the code generation?
Yeah. Okay, so I guess a bit of a long answer. Actually, on a brief aside, like so I was, puzzling about the same thing, and like you get all these language models come out, and I remember one of the questions I tried on ChatGPT, I think this was a swimmer is swimming across a running river to a point across the thing. It's standard, like sort of like math, problem in high school or whatever. The river flows at 5 meters per hour. Swimmer swims at 10 meters per hour. I guess that's a pretty good swimmer. No, it's a pretty slow swimmer. How far does he swim to get across to a point across on the bank and come back? And honestly, this is a question that I think actually people, if you met on the street, if you ask them, they won't answer this question. It's people you forget it from high school, or we just like never paid attention in math class or whatever. ChatGPT came up with the answer, but the wrong answer. It came up with a fairly convincing reason why the wrong answer was the answer, but it was anybody who sort of had like pretty decent high school math would have realized that the answer was like wrong. But it gave concern. And that was probably the biggest giveaway that was like not human, right? Like, I mean, like being so convinced that you're right, but about something that, you're wrong is like an interesting like tell of these generative approaches, because there's no fundamental underlying logic. There's no knowledge of like being stuck in a wrong answer. Like a compiler tells you when it like can't compile your program, like it fails to do it. It doesn't guess what you want to do and get it right. It just says I can't do it. And I think that sort of guardrail is not there in these models, where they don't know when they haven't been able to do something. Now, putting logic in general, though, seems like, I mean, we're almost starting in the wrong place, right? Like the structures are just not there in the language model. We're talking about next word, next token prediction as kind of the way we're training it and so on. So kind of translating this a bit into the space of code generation, like one sort of approach that I think is interesting for code generation, is very different from the current language model thing, is actually all of our languages, like most modern programming languages, they're defined by some kind of grammar tree. And there are production rules, right? Like, you have an if statement, and the if statement consists of if, then an expression, then something, then blah, 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 these blocks, and you keep expanding them. And you can think of training a model that's more like a reinforcement style, an RL style model whose only job is to make expansions in the BNF grammar until it terminates. So such a model is guaranteed to produce at least a grammatically correct program. You can further constrain it that, it must use languages from like the scope and context that it's currently operating in. And so it'll never, it'll be a runtime correct. Sorry. So I think that's a different approach, but I think all of these other approaches unfortunately suffer from the thing of complexity. So like there's certain beauty, right? Like if I take any programming language, I don't have to worry about grammar.
We really try to make if the model is wrong, we want it to know that there's a high chance it's wrong, or not be confidently wrong. So it's interesting that at least so far the way these large language models work, they don't have anything like this feature that they're often very confident they're very wrong and have no idea that they're very wrong. But yeah, so maybe this is a good segue into code generation. So this is definitely a very compelling application of large language models. And on the one hand, I'm actually curious your thoughts on what do you think is, do you think code generation is easier or harder than just language, like other tasks for language models that are more full English, like document summarization or chat responses? Because on the one hand, English is a much larger corpus or much larger language, and code is a much smaller language. But on the other hand, we need to be completely correct. So if the code has just a single error, then it'll error out.
Yeah. Yeah. So I think there's definitely this dichotomy, right? So one also, I think to produce like syntactically correct code is actually much easier, because the domain of coding languages is much smaller than English, right? Like the number of like sort of like legal phrases or structure of the programs tend to be like quite rigid. And so I think being syntactically correct in code is that's the easier part of the problem. I guess it's a bit of a hierarchy. Syntax is probably the easiest, and grammar is probably a little bit harder, but again, relatively easy. Like the grammar codes are grammars are strict for like programming languages. So I think the producing code that compiles part has like definitely that ship has sailed. Then comes the next set of rules, like something that like will run at all. And surprisingly, I think even that is easier than like most than one might first imagine, because like mostly the rules of like code that runs is like you can't refer to a variable before. Like if you're producing syntactically correct code, as long as you're not having like unbound references, it will do something. I think then the big gap in programming is like do something useful. And that's where I think it differs a lot from English. Because I think a lot of English text, once you produce it, if you produce something that's readable by humans, can very quickly become, very quickly become useful. We see it even with humans, right? Like most people can like read something on Wikipedia and not be an expert in the space, and then still like give you a reasonable summary description, tell you what they read and so on. Like my son has read about like RSA encryption like on Wikipedia, and he gave a class presentation. I guarantee you he cannot like encode like a message using RSA like prime numbers. Like it's a bit, there's a big gap between being able to like encode a message using RSA encryption and being able to like roughly understand that RSA encryption is built on the idea that prime numbers, like large numbers, cannot be easily factored or it's NP complete for factorization. So I think that's kind of a bit of the uncanny valley, the chasm to cross with like program generation. I think that program generation in domains is going to be very effective, right? Like so, if we limit our model to having to produce code snippets in a domain where it has a lot of context about what it is generating, that seems much more feasible. I think DeepMind and all are already like tackling the program problem of like generalized like program to like solve computer programming. It's reasonably successful, but honestly, like the kind of amount of compute that's throwing to like solve one problem is crazy, right? Like, so they generate these millions of programs and kind of like run them all and see which ones run and which ones give the correct answer and then submit that. That's like a very expensive like data sort of like compute like intensive way of saying that you solved the generation of programs. But it is certainly an interesting area of research. I think the immediately pragmatic thing is we can definitely go beyond like autocomplete, code complete to like, actual like useful workbenches that are driven by AI to like really speed up like the workflows of like programmers, data scientists, other operators in the space.
Mm-hmm. Okay, so you're saying that maybe there's still some time before we can create a language model that's a general generative code model, but maybe in certain applications where the domain is a bit smaller, there's already some results coming out. And yeah, I know AI assisted data science is quite an interesting area of focus here. Do you think that language models will start to change the way that humans do data science in the future?
Yeah, I think that like in every domain, like I think definitely language models are going to help out here. I think that many different dimensions, but just in terms of like the data scientist workflow, I think there's a lot of like it is convenient to be able to like prompt a system using much more concise statements than like actually elaborate pieces of code. Much easier to say, show me some breakdown by country than like type out the full expression. And like having a language model that can like turn that sort of like open-ended loose statement into like a concrete expression seems definitely within the, seems very feasible now. I think the one interesting area that there's really, I think that there's opportunity for innovation here is if you think about like the kind of like when large language models they train on a lot of text in web pages. So one of the things they don't train on is actually like the data underlying data science, right? Like, so like reacting to what the contents of the actual data are and then producing their output. So I think there's a whole opportunity out here to train models that are a combination of natural language and contextual information that's not like language, but actually properties of data, and then having the model generate useful bits of code to interact with that underlying, whether it's a data warehouse, a model, a table, or whatever. So I think there's a hybrid style of input here where there's a natural language, like prompting aspect of it, context of like what was going on, what the workflow was, but also the underlying data that you're working on so that, the model can build this with it.
Do you think I just have a follow-up. Do you think the most useful paradigm would be the model interacting with the raw data or certain meta features of the data or summarized versions of the data?
I mean, for pragmatic reasons, I would certainly say like the model would be summarized features. I mean, like we talked about like context length as being a major issue with like transformer architectures and transformer cost. But longer term, I think actually something more like, not that the metadata features have to be provided, but maybe the model can go execute operations against the data. So like, let's think of reinforcement style, other side model, and it's trying to generate some prompt. Like you can first choose to issue a query against the data, get the responses of the query, pass that as inputs to its next state, right? So the model can generate the meta features it wants by executing some operation against data itself. Like it doesn't have to have those meta features supplied to it. I would think that like, as we innovate in this space, we want to get to that space where like the model is not really consuming data and just spitting out an answer, but it's actually executing operations against the data to build its answer.
Mm-hmm. Got it. Okay, so maybe we should move on. I know we want to, it'd be interesting to discuss some other topics. For example, other domains where pre-training works well. And also at the end, we can talk a little bit about automated machine learning and how that fits into language models. So yeah, maybe I can kick us off in some of these other domains where pre-training helps a lot. So and one area that I've been working on recently is in tabular data. So here on the research side, there's been an interesting history where gradient boosted decision trees like XGBoost and CatBoost work really well on many tabular data sets that we encounter for classification and regression and these types of tasks. But there's always been a big push to make deep learning models competitive with and outperform the gradient boosted decision trees on tabular data. So, and in fact, in the research community, there's been a lot of back and forth recently on neural nets versus boosted trees, which one is truly better on tabular data. And some of the neural nets are these really sophisticated methods, but even more recently, what we're seeing is this new message that maybe both gradient boosted decision trees and neural nets are reaching the limit of what can be accomplished when using a single data set before we do something else like pre-training or using a foundation model. Like in some sense, if we measure something like the aleatoric uncertainty of the model we have trained, but basically what this is saying is that we've explained everything that's possible to explain, and everything else is just random noise that we have no hope of explaining. So that's why I think foundation models are quite promising even in areas like tabular data, because although we cannot go any further limiting ourselves to a single data set, if we look at tons of other tabular data sets that we've looked at before, we notice general trends in what we want to learn, and we can push much further than a single data set. Yeah, and I also think there there might be interesting applications in forecasting. Do you have any thoughts here?
Yeah, so I mean, I think broadly, like domains where there's a relatively like common way of expressing the problem, right? So like language has it, like solid text, blocks of text. Forecasting is also nice like that. It's a simple problem to state. It's usually, especially single series forecasting, there's a clear idea, right? You have some history, you're trying to predict the next point of the history. Also, they're fairly amenable to like synthetic data. Like, you have the opportunity to generate synthetic data sets. This is not limited to forecasting, but like many models which are simulatable, or many domains where simulations exist, so high fidelity simulations are possible. You can generate a lot of training data that like models can learn. And then in some sense, you're generating data that you're then training a model to learn to invert the function. So you have some kind of opinion about like what kind of functions are there, and then the model has to learn to like invert the function. And I think there's like what you specifically called out. Most small data sets, even if there's a pattern, are not big enough that you can reliably believe that you learn the pattern. It's too easy to overfit the data set before you actually learn the underlying series. But you bring a model that's been trained on some like large prior of like what are reasonable things, in forecasting, it might be some kind of seasonality pattern, some kind of autocorrelation extents, trend terms, and so on. A model trained on all of this, and then it predicts on your small data set without being thrown off by noise that is irreducible noise in your data set that would not allow a model to be trained on such small data. And actually, we've seen the same thing happen with language models, right? So like training a good model to like classify text on a corpus of like 1,000 documents is like impossible. I mean, it's like really hard because English is so noisy. There's so many different ways of expressing the same thing. But now we have like these models that have not been trained on these large data sets doing better on these small data sets. Sorry, I mean, models trained on large data sets, never having seen the small data set, still doing better on the small data set than even like models trained straight up on them. And that's because they've learned all of these properties of English outside of like the thing, and then are able to apply it directly here, right? So I think the same thing applies in these other domains where there's room to like learn about general things first, and then just go ahead and infer on the small things. And like you mentioned, TabPFFM was a good demonstration of that.
Yeah. I think one of the works I was implicitly talking about is this breakthrough result called TabPFFM, where a lot of other models for tabular data in the past have followed the standard machine learning paradigm, where you have a training data set and then you train a model on the training set and then predict in the test set. But this new work, TabPFFM, which came out of the University of Freiburg last year, they do a lot of pre-training. So they take a transformer model and they give it data sets as input, and the model learns to perform Bayesian inference. And so the way this works then is if we get a brand new tabular data set that the transformer hasn't seen yet, it will in a single forward pass, it'll basically learn the decision boundary and then make predictions for the entire test set. And this all happens in just 1 second. So it doesn't need to do any sort of training routine. It just does a single forward pass. And yeah, as you say, I think this is definitely quite an interesting next step because we can learn general trends about how tabular data works and break out of the bottleneck of just learning on a single data set. Yeah, any other insights about other domains where pre-training and foundation models can really give us a lot of leverage?
So I think we've seen this in self-driving too. I think there are companies that specialize in generating synthetic data for self-driving cars and for them to train on. So I think that's pretty well established. I think there's a lot of domains in physics, which is kind of like dear to my heart because I'm physicist by training, but like where there are a lot of problems where we have techniques that can solve them given sufficient compute, but there's a lot of opportunity to like have models that are able to like compress that whole operation into much less space once trained. And it's again like language models, data unlimited, right? Because you can generate any amount of like simulation data that you want for some of these things. So that's another domain that I think is quite promising for synthetic data and for like language model. Sorry, for pre-trained models. Beyond that, I do remember a paper from MIT that like recently came out where they even showed like models trained. Oh yeah, here's an interesting point about synthetic data. So I think that this paper discusses like how a model trained on synthetic data did better than a model trained on real world data. It was in the vision space, there was something specific. So of course you can't draw too much sort of like conclusion on that, but like real world data has this property that there's irreducible noise. And very often when you're training models that are large, training models and thing, that irreducible noise can make leads to all sorts of problems, overfitting, deciding when to stop, deciding on the right model size, model capacity, all those things. One of the nice things about synthetic data is you know the exact answer. Like you by definition define the exact correct answer. And as a result, you can much more safely train like really large models without the danger of like overfitting and so on. So I think that's another definite area that's like very that makes this thing promising. I think to some extent you would even say like the other landmark models like the Go model that AlphaGo and so on are in some sense just like they're specific to Go, but they're trained on synthetic data. Like you can play infinite number of games against yourself. Like you it's just a matter of like producing thing. And so in that context, like even this generation of programming languages and so on, generating programming languages is probably a place where with some cleverness you can generate a lot of useful synthetic data and teach models how to produce that code in a more efficient way than your synthetic data generation, which might be very expensive, but then once trained, the models are effective.
Mm-hmm. Yeah, I like your point about how synthetic data is often more useful than real data, because in real data, our test sets have noise in them, which can actually slow us down quite a lot in certain contexts. But for synthetic data, we know the exact right answer because we synthetically generate it. So if we have a good model for generating synthetic data set for a certain task, like tabular data, then we can often do better than just training on real world data. Okay, so now we're nearing the end of our session. Maybe we can talk about AutoML and how this applies to language models and generative AI. I think it's myself having a lot of AutoML experience. I think language models are quite peculiar because in many other areas, we're trying to build more complex models and search for better architectures and better hyperparameters to train some data set we care about. But with language models, really it's gone in a very different direction, where just training one model is so time consuming that we really can't afford to search over the best models, because it would take a fortune of compute and the computational resources to do this. Yeah, so I wonder if you have any thoughts on how AutoML applies to language models, and if you think we should focus more on just engineering efforts and gathering more data in a smart way, or if you think AutoML has a role in language models.
I think it clearly has a role, because in the sense that Chinchilla, or the paper that like DeepMind put out, like was in a sense like an AutoML paper asking the question of how big the model should be. I think the interesting aspect of AutoML in language models is you're about to go and spend a lot of money training one of these models, and so I think the whole question of like how can I spend a little bit of money first before I make this really big bet, it becomes the core focus of AutoML. I mean, in other spaces where, you know, the wall time and compute time are not really material compared to human time. So, you know, I mean, the number of hours I have to get a person to look at this, it becomes much more about like exploring the space, finding the very best model that can fit my particular data set. Those are the kind of questions that dominate. And the AutoML itself is the dominant part of the cost of the problem, right? Like the AutoML is in some sense like what is you're spending your money on. Of course, each one of those is like individual training runs, but like you kind of see it all under that bucket. But I think like in the language space, it feels more like I do my AutoML on some small set, and I better hope I'm doing it in a way such that it lets me project, I'm going to do this one training run. That's all I can afford. At the end of it, it better have been my best shot. Like I better have picked the right architecture at the start of it, because at the end of it, I'm down. And, you know, I've kind of spent all my money that I had planned for this project. So I think that is, I mean, not that AutoML hasn't worried about these kind of like compute costs and so on. It has very much, but this specific sort of like, you know, goal of like in a small space, in a much smaller space, determining the projection. I think the Chinchilla paper is interesting because it kind of establishes these broad general scaling laws that almost seem like model independent. And so I wonder if there's more room there like that for that kind of AutoML research, where I can like make some broad generalization about like how training will behave given properties of the data, given properties of the architecture, and given properties, without ever actually running an actual computation.
Sorry, I was muted there. I like the way you think of it. In other areas of AutoML, the cost of AutoML is the amount of time we can afford to AutoML is much higher than the cost of training a single model. So we can do these really intricate optimization procedures. But for language models, the cost of AutoML is actually much, much lower than the cost of training the single final model. So we really need to have very smart, efficient optimization methods, and also really hope that any sort of search we do over a very smaller scale size, we hope that this will scale appropriately to bigger size, and the insights we get from the smaller search will carry over to our full run.
Mm-hmm.